Hello everyone. In this lecture we will look at data wrangling. Data wrangling means that we want to get the data in a useful format, which will allow us to do data visualization and modeling. We will talk about Tibbles, something that I introduced earlier but did not discuss in detail, and we will also talk about tidying data. Okay, so let's continue with Tibbles. Now, Tibbles are data frames. But they are a little different. Now, R is a very old language, and certain things that were useful a decade or 2 decades ago might be a problem today. And it is difficult to change the base R without breaking the existing code. So most innovation occurs in packages, not in the base R. So in this lecture, we will describe the Tibble package, which provides opinionated data frames, and it makes working with tidyverse a little easier. So let's import tidyverse once again. Excellent. Now the first thing we want to do is to look at our iris dataset. So question mark and iris. This is one of the most popular datasets out there for data scientists and for data analysts. So the iris dataset has measurements in centimeters of the sepal length and width and the petal length and the width for 50 flowers and each of the 3 species of iris. So we have setosa, versicolor and virginica. If you want to read more about it, you absolutely should. Just do a Google search and read more about the iris dataset, and you'll find hundreds and thousands of examples already available. So if I want to load it as a Tibble, if you see at the bottom, we can see we have the sepal length, width, petal length, width, and the species like this. So we have 150 rows right now. We can also create a new Tibble from individual vectors, and we use Tibble for this. Let's see how this works. So we are creating a Tibble from 1 to 5. In Y we have all the ones, and in Z we are using an exponential and a plus, just a simple arithmetic operation to get 3 columns. Now do remember that unlike data frames, Tibble does much less, which means that it will never change the type of input. It will never convert a string to factors. It never changes the name of the variables, and it never creates row names. It is possible for a Tibble to have column names that are not valid R variable names. These are called non-syntactic names. For example, they might not start with a letter, or they might contain unusual characters like a space. And for this we use something called backticks. The backticks is nothing, it's just a tick like this. Let's see an example. So if you see here, this is the backtick that I've created, this and this and this. The backtick is also used when you're working with ggplot2, dplyr and tidyr. Another way to create a Tibble is to use something called a tribble, which is nothing but a transposed Tibble, which is called a tribble. And the Tibble is customized for data entry in code. The column headings are defined by formulas. That means they start with a tilde sign and the entries are separated with a comma. So if you want to lay out very small amounts of data in a very easy to read format, this might help you. Let me just give you an example. So here we are creating a Tibble. So we have the tilde sign because these are formulas. And as you can see, the data is in a very easy to read format with commas separating. So this is how the data looks. All right. Let's do one more example. Tibbles have a refined print method. That means that only the first 10 rows are shown and all the columns that fit on the screen. Why does it work like this? Because it is easier for us to work with large data. So when we run this, you can see that we are able to see only the first 10 rows and 990 more rows are below it. Now Tibbles are designed so that you don't accidentally overwhelm the console when you're printing large data frames. Imagine you had 10,000 records and it showed you all the 10,000 records. It would have been so difficult to see all of it. If you want to control the number of rows and the width of the display, you can do something like this. So I'm using my flights dataset now. And now you notice my flights dataset is coming like this. So my n is 10, that means I'm looking at 10 columns, right? And I'm actually able to split it into a second block because I don't have enough space to show all these 10, it's spilling into a second block. Right? I hope this makes sense. Like this. Of course, you can also control the default print behavior. So there are different options available there, but we will not get into so much detail. You can also use R's built-in data viewer, which is nothing but view. I had done this earlier one time, but let's do it once again. So if I just click on view, what happens is it opens the data as a different pane like this, and I can see the data in the viewer like this. So it's almost like an Excel spreadsheet. So far, all the tools that we have learned have worked with complete data frames. But sometimes we might only want to pull out a single data frame. That means we want to use something called subsetting, which means pull out a single data frame. Let's see how we do this. Let's say we only want to get df and then we can say $x. This means it will only show us the value of x. We can also say df and then in brackets we can put x and the same result like earlier. And if you want a specific position, you can say df and then 1 and again the same result like earlier. So this is one way, the second way and the third way. So you can extract by the name or you can extract by the position. And if you want to use these in a pipe, you have to use the special placeholder, which is a period. Let me just show that to you. So if you notice, this time I'm giving a period before the $x, right? And you get the same result like this. Let's just do one more example. Like this. So remember, compared to data frames, tables are very strict. That means that they never do partial matching and they will usually generate a warning if the column you are trying to access does not exist. Now you can consider that as both a good and a bad thing, but that's the way it works. Now we can look at data import. So working with data provided by R packages is a great way to learn the tools of data science. But at some point you have to do data importing, which means that you will have to learn how to import your own data sets into R. But this is a topic that is not required right now. Why? Because we are only working with the inbuilt data sets. So I'll just skip this for now and we will do this a little later. That means how do you load your own data sets? For now, let's come to how to tidy data. So we know that tidying data simply means that you're creating a consistent way to organize the data, and getting the data into the format that we want does require a little bit of effort, but it will help you a lot in the long run. Let's see how we do this. So let's look at library and tidyverse. All right. And we want to write table 1. So when we say table 1, it just gives us country, year, cases and population. You can also do a question mark to see what is there in table 1, right? So this is essentially the number of tuberculosis cases documented by the World Health Organization in Afghanistan, Brazil and China between 1999 and 2000. There are 4 variables: country, year, cases and population. Why there's so many tables? Because each table has a different layout, and I would like all of you to pay attention to this. So this is my first layout, everyone, of table 1. Table 2, as you can see, has a different layout. Let me just expand this so you can see this clearly. Table 1 has country, year, cases, population. Table 2 has country, year, type and count, right? So cases, population are mentioned in 2 rows and the count is mentioned after that. Then we have table 3, which is very different. We have country, year and the rate, which is the cases divided by the number of population. Then we have table 4a, which is like this, where we have country and the year like this. And then we have table 4b, which is like this. So in table 4a, we only have the cases, and in table 4b, we have the population. So basically the data is spread across 2 tables. Now these are all representations of the same underlying data, but they are not equally easy to use. One data set, the tidy data set, will be much easier to work with inside the tidyverse. So remember, what makes a data tidy? So what makes a data tidy? Number 1, each variable must have its own column. Number 2, each observation must have its own row. And number 3, each value must have its own cell, right? These are the 3 things that you have to keep in mind. Now these 3 rules are also interrelated because it's impossible to only satisfy 2 of the 3. Again, what is the advantage of a tidy data? It's a consistent way of storing the data. So if the data is consistent, if the data structure is consistent, it is easier for us to learn the tools because they have an underlying uniformity. The other advantage is that because we follow a vectorized nature in R, using functions like mutate and summary become much easier when you have a tidy data set. Let's look at a few examples. So if we want to compute If you want to compute the rate per 10,000, we can simply say mutate. Now you notice it gives us the rate as the last column like this. And if you want to compute the cases per year, now it tells us the cases per year are 99 is 250,740, 2000 is 296,920. And if you want to visualize the changes over a period of time, then we can create a geom line and a geom point. So I'm creating a geometric line and a geometric point, and the result comes like this. So we have 3 lines for 3 countries, Afghanistan, Brazil and China, and we can see the change over time. So we can see that Brazil, let me just zoom in. So we can see that Brazil has grown the highest, the fastest over time. Okay, now a lot of people might not be familiar with the principles of tidy data, and that's why a lot of data that you get might not be tidy. Data is often organized to facilitate some other use than analysis. So a lot of time the data will not be tidy because the person has created it for some other purpose. That means that one variable might be spread across multiple columns, or one observation might be scattered across multiple rows. So a common problem is a data set where some of the column names are not names of the variable but names of the values. Let's take an example. So if I look at table 4a, and we are looking at pivoting right now. So if you look at table 4a, you notice that 99 and 2000 are coming like this. And each row is representing 2 observations, right? But this is not how we want to present the data. So to tidy a data set like this, we need to pivot the columns into a new pair of variables. So we need 3 parameters. The set of columns whose names are values, which is 99 and 2000. The name of the variable to move the column names, which is the year, and the name of the variable to move the column values, which is the cases. Let's look at how we do this. So when I show you the code, it will make sense. So we are saying pivot underscore longer. We are taking 99 and 2000. These are the 2 original columns. The names go into year and the values go into cases. Let's see the result now. So you notice this data has now shifted into this format. This is exactly what we wanted. It's very similar to creating a pivot table on Excel. Let's do the same thing for table 4b as well. Again, if I show you the basic 4b, it looks like this. 99 and 2000 are in different columns, and table 4b, after we have fixed it, looks like this. If you want to combine the tidied versions of 4a and 4b into a single tibble, then we can use the left join function. It's not very complicated. When you look at the code, it will make sense. So we are taking 4a, which is the pivot, we are taking 4b, and after that we are doing a simple left join with tidy 4a and tidy 4b. So if I run this, you notice we get a final data set which has both the points in it, right? Like this. 4a and 4b have been joined together. The opposite of pivot longer is pivot wider. That means when an observation is scattered across multiple rows, what do we do? For example, let's take table 2, right? And if we simply want to use wider here, we can write table 2 pivot wider, and now you notice, please look carefully, My table 2 originally was like this, year, type and count, but in type we had two items, cases and population. And after making it wider, cases and population are shifted into different columns, one each. So remember, pivot wider and pivot longer are complements of each other. Pivot longer makes the wide tables narrower and longer, while pivot wider makes the long tables shorter and wider. Table 3 has a different problem. Let's see. So if you notice, table 3 has a different problem. We have one column which is the rate that contains two variables, cases and population. And for this we use the separate function, which will pull apart one column into multiple columns. Let's see how we do this. So very simple, I want to say that I want to separate my current column, which is rate, into two columns. One is cases, the other is population, right? And if you notice, let me just do it once again. Okay, it says there is an error. Let me check. So table 3 is okay. Yeah. So if you notice, it is split it into cases and population like this. But how is it working? So by default, it is splitting into any point where it finds a non-alphanumeric character. Like here it was this slash, right? But if you want to use that separation character and you want to define it manually, you can do that also like this. So I'll keep the separation character as a slash and you get the same result as earlier. So if you look carefully at the column types, you will notice that cases and population are character columns. Now this is the default behavior in separate. So if you notice here, this is character and character. It leaves the type of the column as it is. But these are numbers, right? And we want them to become numbers. So what do? We use convert is equal to true, and this means that they will automatically get converted into integers, right? We can also pass vector of strings to separate, which will interpret the integers as position to split at. So positive values start at 1 on the left side, negative values start on the -1 on the right side. Let's take an example. So I'm using my separation as 2 and see the result. So if you notice, my year 1999 has split into two parts, 19 and 99, 20 and 2000, and 00, 19 and 99, 20 and 00. It may not seem very practical right now, but it's good to know that this can be done as well. Now let's look at table 5. Here you notice that century and the year are separate. So we want to do the opposite of separate, which is unite. Again, fairly simple. We can write unite and it creates a new column like this with century and year. Now notice the underscore has been added automatically. We did not define it. But because we don't want any separation right now between the century and the year, what we want to do here is to put the separation as a blank, and this time the year comes properly like this. When you're changing the representation of a data set, there is a very important subtlety of missing values, right? And surprisingly, a value can be missing in one of two possible ways. So let me just write this. So missing values can either be explicit or they can be implicit. What that means is, if it is flagged with an NA, then it is explicit, and if it is simply not present in the data, then it is implicit. Let's take an example. So there are two missing values in this data set. The return for the fourth quarter of 2015 is explicitly missing because the cell where its value should be instead has a NA, right? This one. The return for the first quarter of 16 is implicitly missing, right? Because it simply does not appear in the data set. So a smart way of understanding this is to look at this. We can say that an explicit missing value is the presence of an absence, and an implicit missing value is the absence of a presence. I will not get into the philosophy behind it, but just think about it for a moment and it should make sense. So the way we can make a data set from implicit to explicit, right? Or from explicit to implicit, let's look at some examples. For example, in this one, we can make the implicit missing value explicit by putting years in the column like this. So now you notice we're getting two NAs like this, right? Because these explicit missing values may not be important for other representations of the data, we can set the values drop NA to true to turn explicit missing values implicit. Let's take an example. So I'm using pivot wider and then pivot longer, concatenating 15 and 16, and please see the result. It comes like this, right? There is another thing we can do which is called complete. Complete will also make missing values explicit in tidy data like this. So complete takes a set of columns, finds all the unique combination, and then ensures that the original dataset contains all those values, automatically filling in explicit NAs wherever it is necessary, right? All right, let's see if there's something else that we can do. Before we finish the chapter, let's look at the WHO dataset. So World Health Organization, we have 7240 rows and the columns are country, the ISO country code, the year, then we have the count of TB cases, the country name, the year and the population. So let's look at this data, everybody, WHO. This is how the data set looks. Now it's challenging for us to work with the way the data has been given to us right now. And this is a very real life example. There are redundant columns, there are variable codes that are very odd, and there are missing values. This means that this is a very messy data set and we need to do multiple things to tidy it up. So let's look at the columns that are not variables. So you can see that country, ISO 2, ISO 3 are three variables that are redundant, specifying the country. The year is also a variable here, and we do not know what all the other columns are, right? But if you look at this new SP 014, 014, F014, these are likely to be values and not variables, right? It doesn't look like these are variables. These should be values. So we need to gather all the columns from new SP M014 till the last one, right? And do something with it. So we'll give it a generic name and we'll call it key, K-E-Y. We know that the cells represent the count of cases, so we'll use the variable cases. And there are a lot of missing values, so for now we'll use values drop NA. Let's take an example. I will walk you through the entire code that I've written, okay? So what we're doing is we are creating an object called WHO1, and in this we are using WHO with a pipe. We're doing pivot longer. We're taking all the columns from SP M014 till F65. We are putting these in key, the values to cases, and we are dropping any, right? Let's see how the result looks. And the result looks like this. And I'm sure all of you can see that it looks much, much better. And now we can get a hint of the data structure of the values in the key column by counting them. So we will simply say WHO1, and we want to count the key. And this gives us the count here. So with a little bit of thought and experimentation, you can see what is happening. So the first three letters of each column denote whether the column contains new or old cases, right? So new or old cases. In this dataset, each column contains new cases. The next two letters describe the type of tuberculosis. So REL stands for relapse, EP stands for extrapulmonary, SN stands for pulmonary, and SP stands for pulmonary, diagnosed by a smear. Let me just show you my key like this. Just give me a moment. So view and WHO1. So you notice we have new cases, we have SP, right? And if you keep on scrolling down, you would see that we also have an EP here, right? So like this, if you scroll through, we have SP, EP, REL and SN. And the sixth letter is the gender. So this M and F that you see here, so like F3544, M2534, this is the gender, right? And the remaining numbers give the age group. For example, 014 tells me 0 to 14, 3544 tells me 35 to 44, this tells me 45 to 54, like this. So we need to make a minor fix to the format of the column names. Unfortunately, there's a lot of inconsistency, right? So let's see what we do. I will create a new object called WHO2 like this. And in this we want to mutate and we want to replace new REL with new REL like this. Let's see the result. It comes like this. So what have we done? By replacing new REL with an underscore, we have made all the variable names consistent. And now we can separate the values in each code by using separate. Let's see how we do this. So first we will write a new object, WHO3, and we are separating new type, sex, age and an underscore here. Let's see the result. So it gives us the result like this. We have new type in different columns and the sex, age in another one. Now, do we really need the new column? It's not needed because it's constant in the data, right? Like we only have new cases that are coming here. So let me quickly look at this. So we have 76046 and we can also create WHO4 in which we will take WHO3 and we will only select new ISO2 and ISO3. And what are we doing with these three? We are removing them. That's why you see the negative sign, the minus sign. Perfect. Now let's create WHO5 as well. Now the result looks much cleaner. Country, year, type, sex, age and the number of cases. So it's becoming so much more tidy, isn't it? Now even though I have shown you the code one piece at a time, where we assign each interim result to a new variable, remember you don't actually need to do this. So I'll also share the complete code with you. So this is my complete code, everyone, like this. You can take some time, go through it and just try to see if it makes sense. But this is how very simply we can get a result like this. Hold on, just a moment. So this is a slightly more complicated pipe, right? Like this, right? Same result. Excellent. So we have completed tidy data. We have also seen Tibbles, and in the next lecture, we will look at relational data, which is how to create relationships between different tables.